Okay, guys, let's start. I know it's the last talk of the day and the whole conference, so it's going to be a bit hard. Thanks for coming. So we're going to talk about traversing graphs with Gremlin. If you never used graph databases before, you came to the right place. I'm going to give you an introduction of graph technology, state-of-the-art technology right now. Okay, and I work for DataStax. I'm a solution architect there, and I work with a number of open source technologies, Spark, Cassandra, Solr, and also Apache TinkerPop that I'm going to talk about today. Okay, so I will introduce graphs and explain you what graph technologies exist today, available to you today. Some of them open source, some of them may be commercial technologies. We will talk about one particular graph data model, which is called property graph, and we will dive in a little bit more into Gremlin graph traversal language. So this is probably the most popular graph traversal language nowadays in industry. Okay, and many graph databases support this language. But hopefully we'll have 20 minutes or so, 15, 20 minutes just for running some of the example traversals, and you will be able to see all kinds of features that are available to you today through Gremlin traversal language. Okay, so first question, why graph and why now? Right? We have a number of different data models we use to build databases, to model our data. Okay, of course, the first one could be network data model, hierarchical data model. Those are kind of graph data models. But the first most popular one was relational, right? What we found out, it's not very scalable. It was not built to be scalable, right, to large clusters of machines. So no SQL movement designed key value databases, tabular database like key value like Redis, tabular like Cassandra, document like MongoDB. Okay, and you can see they are shown here based on the data complexity and value in relationships. So the graph one is the most complex kind of. But if you think about it, it's also very flexible, very natural. You can model everything with a graph, right? And if you even look at relational data model, the relational databases, they model using conceptual data models, right? You start with conceptual data model with entity relationship diagram. Those are graphs as well. So graph is ultimate data model, very flexible, very generic, very capable. The reason we are looking at it right now and not 20 years before is that it's also kind of hard to scale, kind of hard to make it perform on a large scale for generic type of problems. Okay, so I'm going to, but you can see that it's very natural for us to think in terms of graph, right? There are a number of applications that will be easy to represent as graphs, as webs, as networks, right? Sensor networks, Internet of Things, social networks, right? We have entities there, we have people, we have connections between those people. There are a number of applications that are related to Customer 360, right? The personalization, recommendation system. Fraud detection is another good application that you can see graph technology frequently. There are a number of other technologies or other applications that graphs are well suited for. In terms of graph technology, we have databases and we have processors. Okay, so databases, they're real-time systems, they are OLTP systems, and here are a few examples. Right, the open source Apache Titan database, there is commercial DataStax Enterprise Graph, there is commercial Neo4j. Neo4j is the most popular graph database nowadays. By the way, I'm going to compare some of them, some of the features a little bit later. Okay, in terms of graph processors, the two popular ones is Apache Giraffe, which is Hadoop based essentially, and the other one is GraphX, which is Spark based. Okay, so these are OLAP or analysis type of processors. They are not real time for analysis that will run for hours, days, and so on. In terms of graph data models, pretty much there are two standard data models right now, and they standardize by different entities. So there is a property graph which is standardized by Apache TinkerPop project. It's open source, anyone can contribute. And the other one is RDF graph. RDF stands for Resource Description Framework. So the RDF graph is standardized by W3C, World Wide Web Consortium, and the data models are quite different actually, but that's not the goal of me explaining you how they're different. I can tell you that RDF graph is frequently used, or it's more popular in academia, in government, while property graph is much more popular in industry, and they used to solve many real life and practical problems. There are, of course, there are extensions of those data models, but we're not that much interested in them. Okay, so in terms of query languages, how you're going to process your data, graph data, again, those two entities define different languages. For the case of Apache TinkerPop, there is a Gremlin language. For the case of W3C, there is Sparkle language. They're designed very differently. Okay, Sparkle is based on pattern matching, graph pattern matching. So you have to define graph pattern that will be matched against the graph, which is sometimes difficult to use. Okay, sometimes difficult to use. It's very well suited for doing something like data mining. You have a pattern you want to find whether it exists or not. But for simple things like retrieving, like writing OLTP query, I think Gremlin is much better suited. And Gremlin is a different language. It's a functional language, and it actually traversal language versus pattern matching. It does have capabilities to do pattern matching as well. Okay, and then Apache TinkerPop is what we're going to talk about today mostly. So we're going to talk about the property graph. It defines the structure, and also talk about Gremlin, which defines the process, right? And again, it's open source project. You can always contribute to it. There is open source implementation of the database, but I'm going to talk about it a little bit later. Okay. Also, Apache TinkerPop, besides being the framework, essentially allows you to define, to design databases, okay, and the processors for graphs. So there are a number of them. They're called TinkerPop enabled, and basically all of those examples I showed you, they are all TinkerPop enabled databases. Okay, some of them may support other languages. Like query languages or pattern languages. For example, Neo4j has, besides Gremlin, it also supports Cypher. And also, for example, Stardog, besides Gremlin, supports Sparkle. Okay, but they all TinkerPop enabled. So TinkerPop gives you a framework to design these kind of systems. In terms of processors or lab system, again, you can define graph computer that is explained in TinkerPop. You can define it using either Giraffe or Spark, and you will have, basically, you will be able to use those technologies as OLAP engines that are enabled by or designed based on TinkerPop concepts. Okay, so the structure, we're going to talk about structure or property graph. Okay, so there will be a introduction essentially to what graph is, how it's represented in Apache TinkerPop. Okay, so initially, right, the first main concept, if you have vertices that represent objects or entities in real life. Those vertices have labels, right? Those are like type of entities or objects, like person, right? The specific vertex or entity of type person. There is a movie, there is genre, user, and so on. Right? So those vertices are not interesting unless we have, of course, connections. But here is an example of API, which is again open source API, how you can add those vertices into your graph. So there is a graph object and there is add vertex method that you can use to create vertices for the graph. And you specify label, okay? You specify label of the vertex. So ID of the vertex is usually generated automatically for you, but you can of course have your own custom ID if you like to, okay? So then we add edges which represent relationships between those entities, okay? Edges, they're always directed and they always have labels. So in this case, we have example of movie belongs to specific genre and user-rated movie, and one user knows another user and things like that. Okay, so usually when you use graph data model, you are very interested in relationship rather than individual entities, right? You don't want to retrieve just user with specific ID, you want to retrieve products that the particular user bought and maybe recommend, maybe find similar users and recommend products that other users like, things like that. Okay, so you're interested in relations. The value is in relationships when you're using graph. This is a sample code how you can create those edges, add those edges to the graph. So you pick the vertex and then you say add edge, so one endpoint, and you specify the label of the edge and the second endpoint. So in this case, we have user 1 rated movie 1, and so on. Okay, so besides that, of course, the name property graph comes from the properties that you can attach to vertices and edges, both of them. Okay, so the property is nothing more but key value pairs, right? Where key of the property is the name of the property, and value can have different data types. Okay, so in this case, now we kind of describing our vertices. So we have a movie with specific title in this example, specific year, duration, country, right? And we have user with specific age and gender, and that user rated movie and left specific rating 5. So that's when you have, so the properties can be on edges as well, okay? So that makes it more interesting and complete. Besides that, usually, so let me show you some code, right? Some API, very simple, right? So use either a vertex or edge and say the property has a name and value. Okay, very simple. But besides that, usually when you designing your data models, you're also interested in things like lists, right? Like lists. So there is a concept of multi-properties and meta-properties in Apache TinkerPop in property graph. So multi-property is simply a property with multiple values. Like in this case, we have budget with multiple values, right? And we have production companies, multiple production companies for this movie, okay? And multi-properties can only be used with vertices. They can only be vertex properties. Also here we have source and date, which are meta properties. They describe other properties. So they attach to properties, not to vertices or edges. Okay? And in this case, we have multiple budgets for this movie, and we have source and date describing each of those values, right? Where that value comes from, there is a specific magazine or newspaper, and there is a date on which it was published. Okay? So pretty much that completes everything you need to know about data model. It's quite simple, but also quite flexible and powerful. Okay? Of course, there are many other things that we may talk about data modeling, how you design those data models, but that not necessarily the topic of today's presentation. That will be a little bit more complex. So here is an example how you create multi-properties and meta-properties, right? So in this case, multi-properties can have two different semantics. It's either list or set. In this case, we create a list of production companies, and also meta-properties, they're just properties that you can define on a property. So this B1 is a property of movie, And then for B1, we create another meta property, source and date. Quite simple, right? Quite simple. Okay, so you can generalize this data model into more or less generic kind of graph, which doesn't have specific vertices and edges, but has labels or types of those vertices and edges. So I like to call this graph schema. Okay, even so, graph schema is not required. It's not part of Apache TinkerPop. Okay, but based on this schema, you can kind of understand what is possible in your data model. It's possible that you will have users who rate movies, who know each other, and then movies belongs to genres, and movies can have actors, directors, composers, and so on, who are people, right? And you also have all kinds of properties that can be attached to those labels, vertex labels and edge labels. Okay? So it gives you a general idea. And during the demo, I'm going to use a graph with similar schema, exactly the same schema actually. We're going to do a few things to traverse this graph to compute some useful information. Okay? So Gremlin, now we have data model, we know how to create our graph. What about traversing that graph or creating that graph? Okay, so Gremlin is open source, defined by Apache TinkerPop. You can influence how it will be designed. It's very expressive language. It's Turing complete, meaning you can pretty much do anything with Gremlin that you can do with Java. Okay, very expressive. That means you can write something that will not be suitable, for example, for OLTP. That's something you may have to use Spark graph computer to execute, something that will be very expensive and complex. It's functional language with fluent syntax. You will see examples, and it has bindings in many programming languages. Groovy, Java 8, Scala, Python, and so on. Groovy is the kind of default or the primary binding that is used. I'm going to show you code that is Gremlin Groovy, but essentially it will also work in Java 8. It's the same type of code. Okay, the same type. There will be any difference. Okay, so when you define traversal, there are three things that you need to work with. Okay, the first thing is traversal source. So it's essentially you take the graph and create traversal source. The traversal source is the beginning of the traversal that knows about graph, and it also knows about traversal steps. It knows how to execute them, okay, or how to interpret them. Okay. Then there are traversal steps, which essentially is a set of or list of instructions that needs to be executed. Okay. So I'm going to explain these steps a little bit later in the next slide, what they do. And there is a traverser. Traverser is nothing more but an object, and there can be many such objects executing concurrently, right? So it's very well suited for parallel and distributed computation. So traversal is simply a program or object that executes those steps, okay? Those steps. There are many, so when you're learning Gremlin, the first thing you look at is those steps. There are many of them. Okay, 5 of them are called Lambda steps, and those are very generic steps that take closures or lambdas as input. And therefore, being that generic, usually you do not use them in real life because the systems that implement them, they cannot optimize them well because they are so generic, they do not usually analyze the code inside of those steps. So therefore, most interesting for you will be derived steps, okay? And they are derived from generic steps, from lambda steps, and we are going to just look at a few of them, okay? There are actually a few dozens of them, but you only need 1 or 2 dozens of them to actually use Gremlin very effectively. Okay. So there are some other steps which are not defined and not derived, and there are also step modulators which are simply they change the behavior of a previous step that you use. So they are like passing additional parameters to the steps. There are predicates as well. Okay. So let's look at some of the steps, before we do the demo, before we go through the some examples and run them, let's look at some of the steps based on this image. So let's say I have my program, my object that will execute instruction. Currently, it's going to be on this movie vertex, right? This gremlin is on the movie vertex. And then I tell that gremlin to execute, for example, in step. Okay? In steps pretty much means that it's going to traverse incoming edge, the edge that goes into this vertex, and the traverser, the gremlin, will end up here on the user vertex. Okay? There is also out step, which will traverse outgoing edges. And the traverser will end up on the genre and person. So there will be two of them. The traverser will clone itself and will send them to different edges. Okay? Then you can use both step to traverse edges in any direction. Okay? You can use also in E, out E, and both E to go to the edge itself, okay? Which may seem to be strange at first. Why would you want to go to the edge and not to the vertex? But the reason you want to go to the edge is usually because edge has useful property that you want to access, okay? That you want to access. So these are very simple steps to navigate in your graph. They are called vertex steps in Apache TinkerPop documentation. I like to think about them as navigation steps. So you can go from one vertex to another or to edge. Now, if you end up on the edge, okay, on the edge here, and you want to go back to the vertex, there are steps for that as well. So you can go to outgoing vertex, out V, incoming vertex, or you can go to both V. Again, both V will clone this object, will split it into two, and you will have two gremlins, one per vertex. Okay? And in general, you may end up with many gremlins on the same vertex when you have a little bit more complex traversals. And when you have that situation, they may be actually bulked, or they may be, the correct term is bulked, but you can think about it, they may be merged into a single object. That's another possibility. Okay, so let's look at this example. Here we have the sample traversal defined here. So we start with traversal source G. We have using V method, which will essentially we're saying we are going to start with all vertices. But then immediately we say vertices that have title Alice in Wonderland and year 2010. So it's like a filter in there. We only want those vertices. That will ensure that we will end up on that vertex movie, okay? On that vertex movie. That's where we start. From there, we're going to traverse outgoing edge with label director. We're going to go to the person vertex. And from there, we are going to access the value of the name property, which will be, in that case, the name of the director, right? Now, if I'm going to change this little bit, I'm going to add another label that I want to be able to use in my traversal. Then when I go from the movie, traversing outgoing edges, I now traverse director and screenwriter as well. So I splitted my gremlin into two, and they now on two different vertices, and then they go and access names of those people, okay? So I'm going to show you a demo. So what I showed you is very simple, right? Very simple. Some of the things that you're going to see will be much more interesting than that. But we needed to start with something for introduction, right? So for the demo, I will use DataStax Enterprise Graph, which is a commercial system. But I'm not going to use any features which are not available, which are different from open source Apache TinkerPop. Okay, it's a real-time graph database management system, so it's a OLTP system. It has superior scalability, high throughput, other capabilities like security, search, analytics, and it's also built on top of some very interesting technologies that you may have used or at least heard about. Okay, so as a black box, your application will interact with DSE graph, DataStax Enterprise Graph, using the TinkerPop API. So essentially, you can take any TinkerPop enabled database and you will be able to switch between them if they are truly TinkerPop enabled. So all of them have the same API. The only different API that I'm not going to talk about is this Schema API. So that's unique for DataStax Enterprise. The reason why it's there, why we have Schema, is because the data is actually stored in Cassandra, in Apache Cassandra. So based on the graph schema, there is a database schema created for you in Cassandra. It's also indexed, the data, so your graph is indexed with Cassandra indexes as well. It's also indexed with Solr indexes, if you choose to. And then there are two execution engines, one OLTP, another one is OLAP. And the OLAP engine uses Spark. So it's simply the Gremlin traversal is translated into Spark job, and that Spark job is executed on the Spark cluster. Okay, all of that is done, however, using this middle layer, which does all of this automatically for you. So it takes the schema, data, queries, so again, you only work with with concepts of property graph, with concepts of Gremlin, but internally you have Cassandra, Solr, and Spark integrated and running together, and there are SQL queries being executed, there are Scala jobs running in Spark, and there are Solr indexes. Okay, so I told you that I'm going to give you a little bit of comparison for those existing systems. So in this example, so the DSE graph is compared to Neo4j and also Apache Titan. Apache Titan is open source database. In fact, the same people who built Titan initially, they are now building DSE graph. Okay, and Titan has so Titan is available for free. It's open source, right? You can contribute to it as well, and it has multiple backends. In this case, we show in comparison with Cassandra and some with other backends, for example, HBase. Okay, what you can observe here is DSE graph has very similar features as Titan with Cassandra. It's masterless. All of them actually have open development. All of them support Gremlin. And Neo4j also supports Cypher. All of them have tunable consistency model except of Titan with HBase. The scaling method, however, different. So DSE graph and Titan, they pretty much have horizontal scaling, which is great for us. But Neo4j is going to be scale up. The Neo4j is not truly distributed system. Even so, you can have multiple nodes in the cluster. Each node will have to have a complete copy of the graph in main memory. It has to fit in main memory as well. So it will be a scale-up solution. Not going to be very efficient in terms of writes. Will be okay for reads. So you can see the difference. There is a big difference between Neo4j and other systems. Also Titan with HBase and other systems. But open source Titan with Cassandra and DSE graph, they kind of have very similar feature based on this. Okay, unless you look at the second slide here. So besides that, the DSE graph supports advanced security features. It has the integration with Spark, with analytics. It has integration with search, with Solr. And overall, the DataStax Enterprise overall is a multimodal solution. So it's not just one database. You think about it. It's a platform that allows you to manage data that may be represented by different data models. It's key value, it's tabular, it's document, and it's graph. Okay, so if you were interested in the comparison, but now I'm going to move on to the demo. So I'm going to show you some of these examples. Probably we will not have time to look at all of them. Okay. Okay, so I'm going to use a notebook software called DataStax Studio. Okay, to do this demo for you. Okay, Apache TinkerPop also has an open source database available to you, but however, that database is in-memory database, so it cannot handle large data set. But you can guess that a DSA graph is able to handle huge data sets because the data is stored in Cassandra, and you probably heard about Cassandra's scalability. So the first step here, or the 0 step, is graph setup. I already did create the graph here. So the first instruction here, we basically setting up some, or specifying some options. Then we create the schema. Again, schema is DSA specific, so I'm not going to talk about it. And we're using, this is another method how you can insert data or load data. And this is open source, Apache TinkerPop API here. So we actually importing graph from the CRIA file. Okay, what we get here is the schema is the same as I showed you in the slides, but it's a little bit different representation. There are movies, genres, person, and users. Okay, and I'm going to, so we're going to first do some statistical analysis and learn a little bit about our graph. Okay, so if you start working with a graph that you're not familiar with, you probably want to do, at the very minimum, the same traversals that I'm showing here, and I'm going to explain why. So the first one will simply execute, we retrieving the number of vertices. The way we do it is we're saying, well, start with using graph traversal source, get all the vertices and count them. Very simple. So we have a little bit, or close to 11,000 vertices in this sample graph. Do the same with edges. There are more of them. I'm running on the local, my laptop, so it takes a little bit longer. 69 of those, of the edges, okay? But then there are a little bit more interesting traversals, like the being able to see how many vertices with a particular label we have, how many users, how many genres, how many movies, and so on. So for that, we're using group count, right? So we have this many movies, more people, and this many users, and so on, right? Okay, so we only have 920 movies, but we have almost 9,000 people in our graph. Okay, in our graph. For edges, the same. The only difference, we start with all the edges doing group count by label. So I'm going to execute, and let's see what we get. Okay, so most of our edges we have rated, with label rated. There are more of them than anything else. There are also many actors involved in this graph. Okay, so those were kind of obvious. The less obvious is this one. This traversal is computing degree distribution, and I'm doing group count by count of incident edges for each vertex. So essentially, how to interpret this graph, right? We have only a few vertices in our graph with, let's say, 300, 150, and so on connections. Most of our vertices have very few number of connections, okay? And if you know a little bit about graph and graph theory, most of the natural graphs that appear in real life, they have this kind of distribution, okay? There are other graphs that, let's say the random graph, if you try to generate your graph randomly, for example, you will have a bell curve distribution, okay? There are some graphs that may have a constant number of, or close to constant number of connections. Those are lattices, for example. Those are usually man-made graphs, like road networks, okay? Like most of the intersections, they have only 4. You can say, oh, they only have 4 connections. Those are also power grids and so on. So this distribution is a scale-free graph. So if you're interested in graph, you can look up scale-free graphs. What are they? They are most common in nature, and they have very special properties. So social networks have the same kind of, they are scale-free graphs. The internet, how computers are connected, they are also scale-free graphs. Okay, so these are, they have special properties, but I will not have time to talk about. Another example, so simple navigation, right? Simple navigation. The question I want to answer, do Uma Thurman's fans know each other? Okay, that's the question I want to answer. The first thing I will do is I will find a person with name Uma Thurman, and I'm going to find this one vertex. So the next thing I want to, so the way I find who are the fans of this actor? Those who rated movies of this actor highly. Okay, so I need to find the movies next. Okay, I'm going to find the movies next. I will use traverse incoming actor edge. I found these movies. Then the next thing I will get the ratings. Okay, I will only keep ratings that are greater than or equal 9. Okay, and I will be able to, okay, retrieve that information. So the visualization takes a little bit time in the web browser, but now I found the movies of that actor and all the users, actually all the edges that have rating greater than 9 for that movie, for those movies. Okay, then I go back to the users and remove duplicate user because the same user could have rated different movies. And I find that these users are not truly connected. They are not at least well connected. So if you zoom in, okay, you will see that many of them are actually disconnected. Okay, hopefully you can see that. Okay, you can also extract neighborhoods. For the sake of time, I will not explain the code here, but you can extract subgraphs. Moreover, you can later traverse them if you like to. So for example, if I want to find out everything that is around movie with title Alice in Wonderland, I can run this traversal and see the picture that looks like this. So I have 2 Alice in Wonderland movies, and I have some actors, I have some users, and I have genres connected. Okay, have genres connected to those. I can also do some classic. Friend of a friend extraction, or friend. In this case, it's a friend of a friend. It's a friends of a random user, and also friends of those friends. So. And I'm using here sample 1, which is basically getting the random user. So if I run the second time, I'm most likely will get a different graph, right? Because the user will be different. Okay. So these are some capabilities you can use. You can also compute paths between 2 vertices. So that becomes, are 2 people connected or not? Okay. In social network, maybe you're doing some kind of fraud detection. Are they connected or not? There is a special step here called pass, which allows you to extract pass as you need to. Okay? So in this example, we are looking for a pass between 2 actors. Okay? So 2 actors, Denzel Washington and Morgan Freeman. Okay? And we can see that they are connected. So from one actor, we can go to the movie, then go to Brian actor, and then go to another movie, and finally find the actor. Okay, so things like that. You can do as well. You can also have larger paths if you need to, which I'm going to skip. You can find also top 10 movies. Okay, top 10 movies, for example. You can order things. you can compute. So this traversal also, it does sound like simple one, but you do have a nested traversal here as an example. So we start with all the movies, we order them by their average rating. But to compute the average rating, we go to the rated edges, get the values of the rating, and then compute the mean. And then we specify decreasing order, and we only want 10. So in this case, if we execute it, we will find these 10 movies that have the highest rating in our particular graph. And there are many other features that I will not be able to talk to you right now, but if you have any questions after the talk. So there is some time for the questions right now, and also if you're interested in continuation of this demo, we can talk offline as well. Okay, any questions? Did anyone use a graph database before? Okay, just a few. Which one did you use? Neo4j, okay.
I actually don't know why.
What types of applications did you develop?
Related to the energy utilities.
Engine?
Energy utilities.
Okay.
And we keep in the graph of station inside of, I do not know which database is used for keeping, but I use Gremlin for making queries to this application. So for me, it's external application on which I keep the network, electricity network, and want to know the relations between stations, etc.
So the key here is relations, right? If you do need to store, for example, users themselves, and you need to retrieve users, and they are not related to many other things, and you probably will be good with key value or tabular kind of database, or relational if you don't need to scale to large volumes. But if you're looking at the relations, if you need to analyze paths, right? It's essentially Gremlin, all the graph traversal, so they are about path analysis. If you have the paths there to analyze, that's where the graph database will be much more usable than anything like relational or key value. Because if you think about, relational does have relations as well, but each time you traverse in that relations, you're doing join. Okay, you're doing join. So if you have the path, like I showed you, had 3 edges, the length was 3, and then you can imagine that you will have to essentially join like 5 tables to be able to retrieve the data. Okay, so okay, I think I ran out of time. Any questions? Yes.
Wait a moment.
1 more minute.
So the graphs that you provided actually have the only one direction, 1, 2. So, but usually graph can connect in both directions.
Yes. So nothing prevents you, of course, to create edges in both directions. Okay. Usually it's not a good practice because most of the time it's simply duplication. It doesn't give you any additional information. You can always safely, so for example, user is a friend with another user. You can always ignore direction in that case, okay? If I'm your friend, then you're most likely my friend as well. So you can ignore direction, like steps in and out, they are directional steps. But steps like both, they do not care about direction. So traverse in any direction. So direction is, you can always ignore it in your traversal. It's not going to be important. Okay. But if you need to create 2 edges in different directions between 2 vertices, that's possible.
Okay, we will stop this moment. If you want, you can continue discussion near the flip chart. So